Thank you. After Andres' highly spiritual talk, so it somehow prompts me to say also something general. So let me just try. So I'm talking today. So the main subject of the talk was this cluster varieties. This cluster, let's say Poisson varieties. And so the main point was that there is some link between this and, I would put it this way, Motivic Galois group. I'll explain what I mean by this. Actually, to be precise, it's Motivic Galois of some field F, some variable field. On the other hand, under suggestion of David about 10 years, 11 years ago, there was another midrasha here, and which we're organizing, and the main subject there was something like that. So we would consider quantum cluster Poisson varieties. And the point, I mean, today, we didn't say it this time, but that's what I thought what it is. So you can say that this is kind of representation theory minus groups. So it's exactly I'm taking from you. And that's what we kind of wanted to develop representation theory as a part of theory of cluster Poisson varieties. And so so it's kind of seems like two different things. But I'm going today to talk about this. But it suggests, in the end, if I will have time, I will explain that this story, when you put quantum here, suggests that there is something which maybe should be called something like quantum Motivic Galois group, which I don't quite have a definition, but I have lots of examples which somehow support this idea. And so I'll try to convey these feelings to you. So I stopped here talking about in general, but just wanted to say the last thing, that what these guys are. So I didn't define them. They are defined starting from a quiver. So the only combinatorial object you need in order to talk about this is quiver. And that's, on the other hand, subject of this conference has many things related to quivers. And so this suggests to me that there may be, and actually after listening to several lectures, I start to think that maybe the relation is more serious here, but I don't know. And on the other hand, this story also was designed to solve some problem in physics, which relates to d equals 4, n equals 2 super Young-Mills. So maybe there is a deeper story, because this one is called class S series. This one specialized to something which Sasha was talking about as a special case. All right, after talking all these things, let me go back to my business. So my business is to explain what's the relation between this and this. And so the first question is, what is this and what it has to do with the subject we were talking about. And so the story is this. So you start with any field F. And one assigned to this, falling inside of Bellingson, some category of mixed Tate motifs. We now know that this is a abelian category. Otherwise, I would say that we know all that, but it's a abelian category of mixed Tate motifs over F. And it's still a hypothetical object, except when F is a number field, when we know everything we wanted to know. And the base property there is that, first of all, there are these objects Q of n, Tate motifs, Q of 1, zeta their powers. And secondly, there was a Bellington's axiom, which tells you what's the X group between them. So the X groups between Q of 0 and Q of n, this is just gamma n is the weight here, for some K-series, K group of F, tensor Q. Now, what it has to do with motifs, so of course this was considered as a cohomology of certain complexes. So these complexes are home in the category of mixed motifs between Q of 0 and Q of n. Again, I do realize that I, of course, don't give anything like hints of definitions, but it's not needed. You just need to follow the formal setup. So it's a
so what is Q?
this is tensor Q.
But I don't understand. You said that category is over.
modulo torsion.
But you said the category is over F.
Oh, Pasha, yes, this is very.
Abelian category over which field?
Pasha, very good question, thank you. So we have here category which lives over every scheme, but in particular we consider the scheme spectrum of F. So this category is a category, if you want, of motifs or motivic shifts over this scheme. That's where the F enters. Okay? Now, the Q is a coefficient. So in this category, we have some objects. So this category is a Q category.
Okay.
So the homes are Q vector spaces. And in this category, for every integer n, we have some distinguished object, which is called the Tate motif, which is the usual one. Q of 1 is your Planck constant. So, but then they live in mixed category. And so we have some homes between them. And their cohomology, so we have these complexes. And their cohomology are precisely these X ties. Okay? So that's the picture. So we have some category, have some complexes, and cohomology of these complexes given by algebraic case theory. Now, on the other hand, there is a fiber functor in this category. Oh my. On the category mixed state motifs. Functor which takes this Q linear category just to the category of vector spaces over Q. And it works as follows. So I probably shouldn't even talk about what the fiber functor is, but I'll just say that if you have some object in this category, it carries weight filtration. So you take group Wn with respect to this weight filtration. And then you take home from your Q, I would say minus 2n would be better, from Q of n to here, and take direct sum over all n's. So this is associated graded with the weight filtration. This is home in your category. This is this is a vector space. I don't even consider this grading. And so that's a fiber functor. And so now comes the group. So you can say that the Motivic Galois group G related to F is just a group of automorphisms of this fiber functor. And it's from general principles, it would be clear that this group is extension of GM by some unipotent group. And so what I'm trying to concentrate on is the structure of this unipotent group. Because it's a unipotent group, we can just consider the... It's not a good idea. Just a second. So by general Tannakian formalism, you can say that this category MT of F by this functor is canonically representations of this Motivic Galois group GF. Okay? So, but if I consider, I want to restrict to unipotent part, then it still catches the category. So the category will be just the category of graded representations of this guy, because the grading will come from here. Anyway, so the point is that this unipotent part, together with the action of GM, which comes from splitting, which is there, it's the same thing as this GF. So it really carries the same information. So let's try to concentrate on this UF.
But this splitting is non-canonical.
Canonical.
It is canonical?
It is canonical. I can tell you where it comes from. It comes from, there are two functors between this category and the category of pure Tate motifs. One is stupid embedding, and the other is group with respect to the weight filtration. It provides you two arrows, because the Galois group of that category is just GM. Okay?
Good question. So if you have a motif coming from a variety, what is its type of?
I don't. It's not quite the right question. So if you have what do you mean motif coming from a variety, it has to be mixed state motif.
Yeah.
The fiber functor group. The fiber functor with group with respect to the weight filtration. Period. It has to be Tate first. So, so if you take P1, you take H2 of P1, you have Q of minus 1. It's just the definition. Okay, so let's make a main notation. So L sub F will be just the Lie algebra of this unipotent group. And yes? Yeah, I know. Yeah, certainly. I know. I'm not going to. I remember that. Thank you. So this is the main object of study, and so we want to know what this Lie algebra is. And so what it is from general principles, I said Lie algebra, let me immediately dualize and make it Lie coalgebra. This is Lie coalgebra. So this, Pasha, you have question related to the lecture?
Yeah, I had a question. So in Drinford's work, for example, when he considers his GRT
Yes.
group, the splitting is not canonical, and here it is canonical. Could you explain why?
I cannot because I'm not talking about Drinford. So it is a canonical splitting. I explained to you.
Analogous setting, yes?
No. Let's not go there. So this is canonical splitting comes because of two factors between big category and its associated grade. Okay, so we have this Lie coalgebra related to field F. I drop writing. I drop F now. So I just put L because it's graded. So its structure is this direct sum of L n when n goes from 1 to infinity. Let me actually put F back. And so this is just a coalgebra. This means that it comes with a coproduct. And so what we want to do, we want to consider the standard Allenberg-Chevalier complex of this Lie algebra, L dot. And so what it is, this is just this L dot, which goes to wedge square of L dot, which goes to wedge cube of L dot, and so on. And it has additional structure because Lie algebra is graded, so we can consider some graded piece of this guy. So let's just consider piece of grading, let's call it n. So this is this guy of degree n. And so there is a conjecture which is not a standard conjecture, and it's equivalent to conjecture that there's a category of MT of F which is sitting is a derived category of mixed motive of F. And there is a conjecture which I strongly support that the X groups between Tate objects in a smaller category are the same as in a bigger category. So there's a conjecture that if you take X groups in MT between Q of 0 and Q of n, this is the same as the X groups in DM, which is given by algebraic theory to n minus 1 and so on, the formula which I wrote down before. So as I said, this conjecture is not a standard conjecture, meaning that it's going beyond what is generally accepted. But if you believe it, then you will see that these complexes, they calculate this complex is quasi-isomorphic to this complex R home in Motivic category between Q of 0 and Q of n. I stress again that this is not immediately clear that this should be so, but okay, we will accept this is a conjecture. Okay, this means that we do know cohomology of those complexes. Now I get to the main point. So this is my Motivic Galois Lie algebra, dual to Z. So all I know about it, I know that it's graded and I know its cohomology. But what I really want to know, I want to know what it is. I want to know this vector spaces, and I don't want to know the brackets, the co-brackets. Okay? And so that's where this is the question which actually implies, so if we resolve this question, then we're going to get applications when F is a number field and so on and so forth. Now, how this relates to what I was talking about before? Remember that last time, yeah.
In your old work that you computed for like Q, right? And you get this, it has to do with the multiple zeta functions and the like, and is that not the case here?
No, it's
it's not like a free algebra on like two generators of degree or whatever, or 3, 5, 7, I forgot.
What Andreas referred to, let me first of all phrase your questions and the answer. So Andreas refers to the question, what will be the Motivic Galois group, not over spec F, but over spec Z? And the answer is given, is known, it's given, that's generated by elements in degrees 3, 5, 7, 9, 11, and so on, which corresponds to odd zetas. But this was the case of spec Z.
And for the spec F?
For spec F, I'm going to tell you.
But that will be somehow related to similar issues like multiple zeta functions or not?
Certainly related, but it's somehow, it's not that, it's, you know, you're talking Z versus arbitrary field F. It's a little bit different by spirit questions. So one is extremely specific and another is quite general. So the answer we want to get in a in a way which works for arbitrary field F. So I hope you will see how it goes. Now, thank you very much for the question, because it motivates me to say what I want to say next. That there is a major thing which I conjecture about this. So I call this Freeness conjecture, which tells you basically what the structure of this Lie algebra is. So it tells you that if you consider the ideal L, not ideal, co-ideal, I'm going to talk about language of co-algebras. So if you consider co-ideal L bigger or equal than 2, and remember that here we have n equals 1 still, then this thing is free graded Lie algebra generated by these groups which were introduced last time, Bn of f in degree n. Okay? Co-generated. Okay? So to your question, Andrei, so before we lived when it was spec z, and instead of all these guys, we have just odd zetas, but still was free. Now we have a much, much bigger object, but the conjecture is that and it's not free. It's certainly not free. But if you consider its if you consider square ideal, whatever it's called, this guy, which differs very little from as a vector from this one, we know how, then it's free, and we basically say that we know its structure. Okay, now the point is that this, how does this work? No, it doesn't work. So the point is that if this conjecture would be true, then the conjectures I was talking about Motivic complex last time would follow easily. So this implies, I mean, I'm just saying that this implies that this B complexes I call BFN, which starts like Bn, going to Bn minus 1 tensor F star, and so on, Hn to F star, are Motivic complexes. Calculate the home we wanted to calculate. So why it implies? Huh? What? So why it implies? Because Motivic complexes, just explained, you have to consider the cochain complex of standard Lie algebra. But then if you try to calculate cohomology of the Lie algebra, which is almost free, which has this big ideal which is free, and you know what the generators is, it's very easy to calculate the cohomology. There is Serre-Hochschild spectral sequence which tells you that the cohomology of your Lie algebra can be calculated as some p-dimensional cohomology of the quotient with coefficients and q-dimensional cohomology of the ideal, which is L bigger or equal than 2. And the quotient is easy, so it is kind of known that L1 is just F star. So going to calculate cohomology of just F star with coefficients in this, and only first dimensional cohomology going to appear. So this will be direct sum of this group Bn's. And then if you see how you calculate cohomology of F star with coefficients this star, I think you essentially immediately will get to this complex, and this is 1-to-1. So you can read this argument back and forth. So this conjecture, by a very simple argument, which I didn't specify but somehow indicated, tells you that that's what we should get.
So Bn are some objects you previously defined?
Last lecture.
Can you remind? Is that
Yes.
too difficult to remind?
Yes, no, not difficult at all. So, and actually, let's just do it. So we have, what's the roadmap of this Lie algebra? So first of all, it has L1, and it's supposed to be F star, because if you write down the cochain complex in degree 1, there is nothing but L1, and on the other hand, it's supposed to be K1. So it's F star. Now this L2 is supposed to be B2, and how I defined last time this Bn, I said that this is just the quotient of the free abelian group generated by F by some relations. And this relations has been defined last time, but it's more or less the functional relations for n polylogarithms. So this was done last time. Okay? So this is B2 of F. I claim that the next guy is B3 of F. And I claim that the story kind of stops here because the other guys will be bigger. Why? Because you are talking about Lie algebra. I'm writing the dual spaces, but keep in mind, you're talking about Lie algebra, which is such that it's still like that, this here. It's generated freely by B2, B3, B4, and so on. So how you can generate something from these B groups? In degree 2 and 3, there's nothing you can do. You can just put B2 and B3. There's no commutators involved, right? But in degree 4, we're supposed to get extension like that. And this is a kind of what we expect, because we have commutators of something which comes from the degree 2, and we get the generators. Oh. And we get the generators, which is my B4. And so this Freeness conjecture tells you that this L4 is supposed to be extension of H2 of B2 by B4. And so you might think that it just tells you what it is. It does tell you what it is as a vector space, but on the other hand, it doesn't tell you how it looks as a Lie algebra, because then it's very unclear how to define anything like cobracket. So you need to define cobracket from this thing, which goes to B3 tensor F star and wedge 2 of B star. And then the very question whether there exists any extension like that, which has such a quadratic, is a very unclear, very problematic statement. It's very unclear whether it should exist or should not exist, and if it exists, why it exists. Why? Because if you try to take it, for example, direct sum, let's suppose it splits, then you have here some subspace which is lambda 2 and B2, and one can easily prove that there is no map from here to here. No map, I mean the following. Whatever I consider all constructions which are functorial in F. Or what is the same, I consider only constructions which can be defined by polynomial equations with rational coefficients. And so I cannot do something for one field and do something else for other fields which are completely unrelated. So it's supposed to be functorial. And then one can prove that there is no functorial map between this abelian group and this abelian group. It just does not exist. So the very question whether you can write any extension like that, which is coming with the coproduct which I was talking about. So my was coproduct. This is a highly non-trivial question whether you can define anything like that. And so my goal is to explain, hopefully by the end of this lecture, that this cluster approach does give you this construction. And so using this, it is using this construction which we prove all the results which I was talking about last time in relation to K-theory and special values of L functions.
So question. So this Lie algebra L, or rather L dual, the whole Lie algebra is free?
No.
Only L2 is free.
Only L big or equals. Starting from 2 it's free. But the whole Lie algebra is certainly not free.
Okay.
If it would be free, then this Lie algebra would have trivial second and high dimensional cohomology. But its high dimensional cohomology are abundantly present because by Belanson's conjecture combined with this non-standard conjecture, they're exactly the pieces of algebraic case theory. For example, the nth dimensional cohomology in V10 are Milnor case theory. It's not trivial.
Okay.
So it cannot be free.
Okay.
Absolutely cannot be free. But what I'm saying here is that it's very close to be free. And this makes all this picture. All right. So, so the next thing which I wanted to do, I wanted to explain how to construct this extension using clusters, cluster varieties in a very crucial way. But since I want to do this, I better to do this in a general cluster setup. So I decided that I wanted to tell you I wanted to tell you how this cluster polylogs, in particular in weight 4, lives on all cluster varieties, rather than give you just one example, which I did last time. So let me talk a little bit about this cluster varieties. But again, remember that the goal is that after a little discussion, maybe like for 10 or 15 minutes, we'll come back to this question, how to construct this extension, and cluster varieties will help us to construct this extension. Also, before I go there, so Andrea asked me what these groups, how they defined. They defined for all n, but remember that the last time, for this particular group, there was a very specific construction. It was the Bloch group, right? Oh, you forgot?
Yeah,
Huh?
I remember the Bloch group.
Huh?
I remember the goal.
Who knows? And it was defined as a quotient of free abelian group by the Abel's 5-term relation. So it turns out that for this group, you also have some very explicit presentation, which is kind of the same spirit as for B2. And so maybe I don't need it, but I just might give it to this presentation. Again, it's not needed for the rest of the lecture, but you might want to see what kind of questions you deal with when you try to define all this when you kind of explicitly. So the relations for B3, they go this way. So you start not from 5 points, not from 4 points originally, but you start from 5 points on P2, and if I said 5, 6. And so let's start from vectors L1, L2, and so L6. And you assign to them something which I call the triple ratio of these functions. And it's defined by explicit formula. It's alternation with respect to group S6 of the following expression, which looks extremely strange. So you put here the volumes. So you have P2 is a projectivization of V3, and it has the volume element, omega 3. And so you put omega 3 of vectors 1, 2, 4, omega 3 of vectors 2, 3, 5, omega 3 of 3, 1, 6, and put in the denominator omega 3 of 1, 2, 5, omega 3 of 2, 3, 6, on omega 3 of 3, 1, 3, 1, 4. Okay, and so you consider this expression. You alternate, and so this belongs to the free abelian group generated by your field F. And so you declare this to be some element in this group. Now the relation is that if you add the 7th point, then alternating sum, I evaluate. Okay, so I cannot write below. Huh? So if you consider the alternating sum of this triple ratio, so whatever, when I meet one of these points, then it's supposed to be 0. I mean, this is the relation and the only relation which you add. So the claim is that if you want to start as a trilogarithm, this gives you functional equation, and any goes from that. Any one is deduced from that the same way as any one was deduced from the 5-term relation.
Well, again, stupid question. What is the motivic meaning of the DI? Are they some sort of child groups?
No.
Can you give a motivic?
No. I certainly can give motivic meaning, but I prefer not to. And all I wanted to say is that they parameterize, they correspond to some mixed motives, to polylogarithms, to motivic polylogarithms. That's their motivic meaning, but I'm not going to talk about this. So this is presentation here, 1, 2, 3, and so you might hope to have something down, and it seems to me that we are not going to see such a picture going down. So what we're going to see, we are going to see a similar picture which goes about else, but not about this B's. About this B's is probably, I mean, you probably can't go to similar descriptions for B7 or I don't know. But for those, I'm going to explain how to proceed then, so how to write the explicit presentation of this shape. Still, so the question where does this formula comes from, so it occupied me for a long time, and then about 10 years later when I found it, so I realized that it does have a meaning. And the meaning is that this is the non-trivial, the only non-trivial cluster Poisson function on cluster variety which corresponds to the root system D4. This is the first one, the first non-trivial function on cluster varieties which does not reduce to cross ratios. The very first. There is no simpler ones. And it's a Poisson function. It's a cluster Poisson function on this variety. And all the properties, it turned out that all properties which I use in the proof of this are actually just properties of the cluster functions. So not more, not less. So that's why let's just talk about these cluster varieties. So as I said, again, for the next 15 minutes, it's not going to be any relation to what I said to you before because it's a different subject. So I will start with a quiver. Few. Now, what is a quiver? So many times it has been discussed in these lectures by Vanya, for example. But for me, it's a lattice, some element epsilon, which is just element in the weight square of this lattice, and a collection of basis vectors. This is basis in this lattice. Why this is so? Because you can write down your standard quiver as saying that this is just the vertex corresponds to basis vectors, which parameterized by some set I. And then the number of arrows from, like, for example, from 2 and 3, you draw as many arrows as absolute value of this tensor in this basis. So you write this tensor in this basis, and they will pick up some integers. This is precisely the number of arrows which goes from here to here. So it's a one-to-one. Okay, now if we do have a quiver, we can assign to it what I would call K2 torus. Again, the quiver is the same thing as the following data. So I call it K2 torus because I really care about K2 class of what I'm going to say. But the data is this. So this is first a split torus T. Secondly, it's a certain class W in which 2 of the field of functions, and the collection of characters, basis of characters in this torus. So this is built in such a way. So this is a torus, split torus. And so the lattice of characters of this torus is lambda. And now W is just encoding this element in language of this torus. So you can therefore write W as something like epsilon ij ai wedge aj. So this lives in wedge 2 of regular functions, multi-group regular functions on this torus. So that's my W class. And so this is just the same thing. So to tell you this is the same as to tell you that you have a quiver. Now, the word K2 here indicates that I'm going to care in the end about data which consists of split torus and class in K2. Class in K2 which defined regularly on the whole torus, so it must have this shape. But now the thing which happens in cluster world that what you can do, you can mutate now. So, so let's consider mutations of these quivers. So actually I realized that
Is the Steinberg relation a special case of this relation or not?
Yes, you will see Steinberg relation in a second.
Okay.
So that's where we're heading to. So we define mutations of quivers. So in this will be mutation of quivers. So we fix some element of your set I. So this basis vectors are parameterized by some set. So we fix this set. And then we define mutation of quivers. So we have quiver Q, and we want to construct a new quiver Q prime. Mutation in direction Q, K, sorry. And so what we do, so what is a quiver? Quiver is a triple. It's a lattice, it's a form, and it's a collection of basis vectors. So when we mutate, we don't change the base, we don't change the lattice, we don't change the form, we change the basis vectors only. And so all I need to tell you who are these new basis vectors. And they're given by something which is called half reflection. So if I is not equal to k, they're just the same vectors. And the only vector which changes is the one which corresponds to I equals k. So it's given by some, I said, half reflection, so formula like that. Okay? So this is a new quiver. So we just change the collection of basis vectors. And then if we calculate the same bilinear form on this new basis vectors, we get some new number of errors between the vertices, and that's my new quiver. Now, this square bracket plus means, first of all, that you follow the lecture, and secondly, that you get an integer here which is taken as is if it's positive and as 0 is as if it's negative. It's a cutting function. So we also associate to this mutation. So remember, there is a torus TQ and the torus TQ prime. And we also want to define some birational map, mutation mu k, between these torus. So it's a birational map. So since it's birational map, the only thing I need to tell you how it acts on the coordinates, on the coordinate functions on this torus. And so here, that's a standard formula, which is precisely the Fomin-Zelevinsky formula, original formula. So this new function is given, it's almost always ai when I is not equal to k. And if it's ai equals to k, then you write down some rational function. So I write this m plus m minus divided by ak. Okay? So this is when I equals to k. And who is this m plus and m minus? Also important. So this m plus, this is the product of the standard coordinates aj epsilon kj over j such that epsilon kj are positive. And we add to it a similar product of aj epsilon kj, where epsilon kj is negative, but then we put the minus sign. Oh, sorry. No. This is a minus is that. Okay? So that's the definition of mutations. And after that, we can start mutating the original quiver, get new quivers with new coordinate functions, then again new quivers with new coordinate functions, and so on. Now to Andrei's question, so where is the Steinberg relation? We can ask the question, what happens if you take the original class W written in the first quiver and subtract from it the class W prime, which is written on the second quiver? Remember that the class W prime is determined, it's given you basically by the form. And so it is for one torus, it looks similarly on the other torus. But if you consider difference, which means that we take W prime minus mutation k star of W, that's what I mean by difference, then that's going to be Steinberg relation. It's going to be 1 plus xk, what it is, I'll write in a second. So I can write it xk, which xk, and this xk is just the ratio m plus divided by m minus. So this is a basic fact which proves you that when you mutate your torus with the form in lambda 2, the class in K2 does not change. But it also tells you why exactly it doesn't change. It tells you the Steinberg relation, which provides you the reason why it doesn't change. And so what do you want it to do now? We wanted to...
1 plus or 1 minus?
This is 1 minus, and in this business, strangely enough, you have to treat plus as minus of minus. And this is secretly also minus. But we really don't care, because minus 1 is an element of two torsion. And we do it modulo two torsion. Okay? So this is this coboundary of the element minus x sub epsilon. It probably shows that the definition of Miller K-series should be a little bit adjusted, so it should be plus everywhere. But because it's very traditional, I just leave it this way. All right, so now we go into play the same game as we played before. So before we have Stashev polytope, and we said that the vertices of the Stashev polytope are triangulations of some polygon, but their main role in life is that they produce some kind of coordinate systems. And then when we change a little bit cluster coordinate system by one flip, then the corresponding class changes by Steinberg element. And what we were doing on the previous lecture, I was saying that we have to go up. So we have to take not only W, but e to W or W square, and we have to see how to deloop the corresponding construction. And so that's what I'm going to do now, but I just want to explain the last thing about this cluster varieties. What is the analog of the cluster of the Stashev polytope? Okay, so once again, so far the main point is that there is a notion of cluster varieties. It's officially defined by gluing all the story. And from this formula, it follows that cluster variety comes with distinguished class in K2. And so what I'm saying here that it not only comes with a class in K2, but it comes with a much, much richer Motivic structure, which I now want to explain. Where is, okay. So the next question was the analog of the Stashev polytope. So this has a name. It's called cluster modular complex. And again, till now, what I'm telling you is something which has been known for a long time, but quite soon I will go to our joint work with Daniel Rudenko. So I just wanted to put it on the blackboard. This is okay. So, okay, we start again with a quiver. So we have quiver, Q, and we want to assign to this quiver a simplex. Just some combinatorial data. That's called SQ. And this simplex has dimension n-1. And it has the following data, that if you consider codimension 1, n is rank of my lattice or split torus. Okay. So its codimension 1 faces of this simplex are in one-to-one correspondence with this set I, which parameterizes the cluster coordinates. So it looks like that. So we have a simplex. But then remember that when we mutate, so we don't change almost all coordinates. We just change one coordinate. And so if you mutate in the direction k, then all other cluster coordinates will be intact. And so we can just glue another simplex here. And so we wanted kind of to put this cluster coordinate sitting at the vertices of the simplex. And so we do it for each of the mutation. And then we keep going. Again, when we're doing this mutation, we're going to get a couple more simplexes, all simplexes attached, and so on so far. So all we get a tree, infinite tree, which grows in all directions. I don't identify yet anything. And so if we do it, like in this case, when n equals 3, so we get the standard picture, which somehow useful to draw on a hyperbolic plane like that. So this is my simplicial complex, which I built from that. Then I'm saying that I wanted to incorporate this cluster function, this bilinear form, as a function on pairs of faces of this simplex. So we define the following thing. We define some set F, which be the set of pairs. It's one of those simplexes and one of the faces of those simplexes, of this simplex. And so here S is S simplex decorated as above, one which we consider here, one of those simplex, for example, this one. And F is just some face of the simplex. So this is my S and F. Now, I wanted to consider the fiber product, F cross F, over this simplicial complex S. This is my simplicial complex, which I built from the simplices. And so all I'm talking here informally, that I take a face and consider a pair of simplices which corresponds to this face. But then my bilinear form produced me a function on this. So the claim is that this collection of disappear from the blackboard. Remember that I have this epsilon, which was given to me just as some skew-symmetric matrix, coefficients of this element lambda 2 or whatever. And so we can consider all of them and produce out of them just a single function epsilon on this F cross F over S. all I'm saying is simple bookkeeping. I'm just saying that we want to produce some kind of single function which encodes all these bilinear forms, all these matrices which we get by evaluating my bilinear form on pairs of vectors. Okay? So even if you didn't completely get this definition, so you only need to know that there is some set and there is some function in this set, and that's exactly what encodes the whole process. Now we define subgroup delta. So it's a group. It's a group of all automorphisms of my simplex S, which
that function linear on the
no. It's a combinatorial object. So once again, so what I had before, I have a notion of a quiver. Okay, quiver is the same thing as Q-symmetric matrix. So a quiver has vertices, and they're just columns and rows of this matrix, and the entries of this matrix, how many arrows you go in positive direction. Okay, so it's just a Q-symmetric matrix called epsilon ij. Now, when I mutate, my basis changes. And so my skew-symmetric matrix therefore also perturbed somehow. So I get infinitely many skew-symmetric functions, okay? For each quiver I have skew-symmetric function describing this quiver. And so I just wanted to produce formally some object which is somehow, which contains information about all of them and nothing else. That's what I was doing formally here, okay? Even if you miss these details of this F, so just forget it. It's just a collection of all these functions, okay? Now I want to consider the group of automorphism of this infinite simplicial thing, which presents this epsilon ij's and also presents the cluster coordinates, because the cluster coordinates, by definition, they sit in the vertices of this simplicial complex. Because when you mutate, we don't change the cluster coordinate, we change the epsilon ij. But so we may find some symmetry which goes from here to here, which, when you pull it back from here to here, you'll identify epsilons with epsilons and coordinates with coordinates. Then we say that's acceptable, that's element of my delta. And so if you get it, just forget about these formalities. So you want to say that preimage of the cluster coordinate is a cluster coordinate, and preimage of this epsilon is epsilon. So this is just the subgroup of symmetries of this infinite simplicial guy, which is decorated by coordinates and by quiver data. Okay. Now I say, okay, let's take the quotient. It's cluster complex. This is a quotient of this simplicial complex by this delta. And the main point is that this is a manifold. This is not yet a manifold, sorry. So we get this quotient, and if you take now what I call cluster star, which is, okay, let's just move slowly. Let's define cluster star as cluster minus, let me just explain without writing this on blackboard. So you have this infinitely many simplices, and so when you look at them, you see that some faces of the simplices, for example this one, appear infinitely many times, and we want to discard those. But the ones which appear finitely many times, we keep. And so, for example, if you take this n equals 3 situation, when we take the simplex which corresponds to upper triangulation of upper half plane, we keep upper half plane, but not the points on the absolute. So this is my cluster star. This cluster minus these things. And the main point is that this is a manifold. That's a theorem. It's non-trivial theorem. This cluster star is a manifold. And now we can take the dual of this manifold. And that's a modular complex. So it's a definition. The cluster modular complex M is the dual polyhedral complex to this abridged cluster, to this collection of quotient of this infinite cell complex by delta.
So what are the spaces?
What?
What are the spaces of the complex?
Sorry. It's a polyhedral complex. So, for example, here, this is a tree. This is what we get.
Chain what is it?
No, no.
It's a cell.
It's more than cell complex. It's a polyhedral complex. So it's built from polyhedrons, not necessarily triangles or this. It's built from polyhedrons. So it's a cell complex, and then there is a main theorem about the cell complex: is that any face of M is a Stashev polyhedron. That's important for me. Of type ADE. There's notion of Stashev polyhedron which you get to other root systems. Okay, and so this is the guy where we're going to perform the construction. So we want to now take this guy, and we wanted to start doing this delooping process of W square or W cube related to the simplices of this guy. And
So what kind of manifold is it?
it's not a manifold. You see, it's a tree. Tree is not a manifold.
What you said, cool star is a manifold.
Cool star is a manifold like this upper half plane. So in real life situations, looks like Teichmüller space in some examples.
So it's contractible.
It's not true that it's always contractible, but it's supposed to be true. Unfortunately, wrong, but it's close to be true. Okay. So now I want to say, this is going to the end. So I wanted to start doing this construction of the looping of my e to omega, but in one particular example. So I wanted to do this in weight 4. So in weight 2, this is basically what I did last time. And I can do this again. I can just say that in the weight 2,
The idea would be that some homotopy group of this manifold that all relate to give you some relations.
not homotopy group of this manifold, this is not quite a manifold, it's a polyhedral complex. But this, not the idea, but the statement is that the chain complex of this polyhedral complex maps to the Motivic Lie algebra. There is a map. And so we are going to start, maybe I should write this down, that there exists a map of complexes. So you take the chain complex of this polyhedral thing and you map it to the Chevalier-Allenberg complex of this Motivic Lie algebra. And if I want to tell you the truth, we're mapping here to some subspace because where it's some manageable subspace which conjectures the whole thing, but it doesn't matter. So you map, it's in the end it's still
Depends on the quiver. So you choose any quiver?
yes, any quiver. And so if we want to do this in degree 2n, then it has a property that if you start with a vertex of this cluster polytope, which is just a quiver, this is the same thing as quiver, then this, and this is the initial part of the process, goes to this w v raised to power n, which belongs to wedge n of the field of rational functions on the corresponding cluster variety, sorry, f, field of rational functions on the corresponding cluster variety which relates to this quiver. So there exists a map like that which starts with wn. And so now let me just exhibit this map, and in the end then you will see that I'll write you some formulas, sorry about this, but in the end of the day you will see that I will define L4, and this is exactly what allows to prove everything which was needed to prove. So
The C of L is completely combinatorial. It doesn't
absolutely, absolutely,
Does not depend on.
absolutely, yes. So the construction is it's a universal construction, so you'll see it. Okay, so we assign now we assign to this vertex, as I said, we assign w square. Now
This
what
map is factorial with respect to F.
you will see from the constructions that it is. So let's suppose that we have two vertices. If we have two vertices, then we have two w elements, w1 and w2, and they are related by the HE. But if you still remember what I was telling you minutes ago, you might remember that the HE gives rise to a function x sub e, which is ratio of this m plus by m minus by definition. So there is some canonical function which you associate to every h, and this is the one which gives you the Steinberg relation. And so we assign to this h the following expression. it's minus x sub e. Tensor, I'm actually doing this in general, so let me do this. Let's assign to this e to, for now, let's do e to w. It will look simpler. So then it will be here e to w1 plus e to w2 divided by 2. All right. Now, what if you have a square? Because in this polyhedral complex, all faces are Stashev polytopes in degree 2 is just squares and pentagon.
This curly bracket is Steinberg?
Yes, this is a Steinberg multiplied by the exponent of the wedge 2 element. So this lives in the corresponding part of the Motivic complex. So if you remember how Motivic complex looks like, it's a chain complex of this Lie algebra. And so we take from this only element in L2 tensor wedge powers of f star. Okay? Now, what's going on?
You need Q coefficients for this, or-
Yeah. I need Q coefficients. I definitely need Q coefficients. So here we have 4 vertices. W1, W2, W3, W4. And this is going on to x sub E1 sub 2 wedge x sub E3 sub 2 tensor e to W1 plus e to W2 plus e to W3 plus e to W4 divided by 4. And this leaves in this B2 wedge 2 star something of f star. This exponent gives you the tail. Okay? Is that clear? Okay.
Is it some calculation of Poisson brackets or is it
It's a calculation. Now, what's going on to pentagon? So if you have a pentagon, then you have 5 vertices, so you have 5 W guys sitting here. But you also have 5 edges, which means that you have here 1, 2, 3, 4, 5 this x coordinates. So have here, for example, this edge sits x1, here sits x2, here sits x3, here sits x4, here sits x5. And so we assign to this the guy which is minus xi sub 3 tensor xi minus 1 times xi plus 1. This is element in B3 tensor f star. Tensor e to something which relates to this phi gon. I don't have time actually to define you something, so I'll skip it. But there is some very, very simple element in wedge 2 which you can cook up out of this data. But what's important where it lives in B3 tensor f star tensor wedge of f star. And so now we come to the main point. So we want to know what's going on the associahedron part. And here is what is going on there. This is 3-dimensional part. So, sorry, I'm a little bit out of time, so let's just write. Huh? So now I want to do only the case when k equals to 2. So with wedge square. And so what happens is that we have associahedron is dimension 3 Stashev polytope, and which sits as a polyhedron on our cluster complex on cluster variety. So it looks like that. And now what happens that to every face of this guy, we associate something which lives either in wedge 2 of B2 or in B3 tensor f star. To every wedge, we associate something which lives in B2 tensor wedge 2 of f star. To every point, we associate something which lives in wedge 4 of f star. Now the question is, this guy, what it corresponds to? What is the guy which corresponds there? And so here I'll just write down some kind of formula. So the formula tells you that you have to start with a combinatorial data, which is a hexagon. Okay. It's a hexagon, and so it's numbered by 1, 2, 3, 4, 5, 6. And I want to associate to this hexagon some kind of function, so to speak. And so it works this way. So you choose one of the diagonals of the triangulation. And then you assign to this, again, I write in formula where I didn't quite explain what the meaning of the sign. But to every I'm kind of mixing languages now. Let me, just for simplicity, assume that I'm sitting not on arbitrary cluster variety, but I'm sitting on the space which is conf 6 of P1. So the formula, it's faster for me to say what's happening there. So then these points are just points on conf P1. And so there are two cross ratios. There's cross ratio which corresponds to cross ratio of those points and those points. And so I just put them all right. So I write some kind of new functions like 1/3 logarithm, which corresponds to 1 cross ratio of the first 4 points, comma cross ratio of the last 4 points. And then this is arguments of some function which I didn't quite define, but I'll tell in a second. And then you just do all the cyclic shifts. You can just rotate this picture cyclically. So you get some kind of function. And then you suppose also to add here some strangely looking expression which lives in the group before, cross ratio of some guys. This is 4 logarithm plus some other 4 logarithm, which it's some kind of, again, analog of the cross ratio here, which I don't want to maybe define in a second. So you consider some simple expression like here. So the only trick is that I didn't quite define where this element xy through 1 lives. I mean, I need to define how it co-multiplies. And the main point is that it co-multiplies to just x sub 2 which y2 here, and some very easy formula there. So just some very explicit function, motive which corresponds to some very explicit function. So now I'm saying that that's it. So this is a function which makes this diagram commutative. So the main point that it makes diagram commutative means that if you go to the next Stashev polyhedron, which has 7, which Stashev polyhedron which is 4-dimensional, then alternating sum of this of 7 functions like that is going to be 0. So you produce a functional relation. So what I did, I produced and proved functional relation which relates this kind of new function which we introduced here with the 4 logarithm. And I claim that that's it. That if I consider just a single functional equation, so basically I'm saying that I can define my L4 as just the following guy. I take free abelian group which morally corresponds to all 4 logs, and I take tensor square of free abelian group which corresponds to this new function, and I define by this 7-term relation which I just produced out of this game. And so I claim that this is the guy which describes L4, that I can define the coproduct on this guy, which is actually built into this picture. And but the main statement is that this guy, this is a theorem about this guy, that this guy sits in this exact sequence, that if I define this way, then the exact sequence in which I want it to have is indeed there and exact. It's certainly not split. The theorem is not split. So I defined such a sequence, and so this is.
What do you mean by not split?
It's not split. Yeah, yeah. So okay, so I'm out of time. So that's basically it. So I defined. Maybe I just say one more word. So I defined this splitting. So this exists on any cluster variety. So this used in the proof. So hopefully we can do this in higher weights. But it also asks for quantum interpretation. So I probably don't have time to talk about this. I can just explain how the quantum dialogues enter to this picture on the way too, and I hope that this story, this very explicit story, hides some kind of higher analog of this quantum polylog identity satisfies. So this time it's not pentagon, it's 7-gon, and the function is not quantum dialogue, but something more sophisticated. But I do hope that this story can be quantized just the same way as the dialogue story was quantized and was a kind of backbone of this quantization of cluster varieties. So this should also lead to some quantum story. Okay, that's it.